Tracking is a process of following the sun's movement from east to west. So during tracking, a collector follows the movement of the sun to achieve beam normal radiation and to minimize the incidence angle. Now this figure shows the schematic arrangement of a typical tracking mechanism. So in this figure, these are the directions shown. This is a east, this is west, this is horizontal. Sun moves from east, it rises from east and then it sets on west direction. This is the collector. This is the aperture of the collector, and then at the bottom of the collector here there is a driving mechanism, chain and sprocket, which drives the collector, which rotates the collector in about its axis. So the collector rotates about its axis here from this point. Okay. This is the position of the receiver. So as the sun moves from east to west, the collector also follows the sun from east to west. So this direction shows the movement of the collector. From this driving, so this is a driving mechanism. This is a chain drive. So chain drive is connected through a shaft and then through a coupling. This is a flexible coupling to accommodate shocks in the starting and switching of shocks during the system. So coupling, and then this coupling is connected on the input side to a reduction gearbox. The reduction gearbox is generally a worm and worm gearbox which has a very large reduction ratio. So of the order of say 2000:1. So one can use this reduction of 2000:1. Why this reduction is needed? Because generally the electric motor used is AC, then the minimum specified RPM of an electric motor is 720 RPM. So 720 revolutions per minute is the input to the gearbox, and this gearbox is required to produce half a revolution, that is 180 degrees of revolution over a day. So one can imagine what is the extent of the reduction needed. So the reduction of the order of say 2200:1 or 2400:1 is needed. In that case, practically the worm gearbox of that reduction in one single stage is not obtained. Then there are two options. One is to get the reduction box custom made, or to attach two worm and worm gearbox in series. So this reduction gearbox is a combination of the gearbox or custom made gearbox which has a large reduction ratio. Now this gearbox receives input from the electric motor. So in electric motor, DC is one option, but DC electric motors are more prone to maintenance. They require frequent maintenance and they are not sturdy in their operation. And again, we need to convert AC supply into DC. So that adds to all the components of the tracking system. So it is always preferable to use a popular synchronous electric AC motor. So this is a three-phase electric motor which receives the electric supply from here, and then it receives the electric supply from control panel. Now this is a control panel to which the mains are connected. Main electric supply is connected. This supply is refined and then it is given to the electric motor. Now this control panel also has the signals of activating signals. So these signals activate the motor and rotate the motor whenever it is required. So how these signals are processed? These signals are processed on the basis of the signals received from these sensors. These sensors are either chronological sensors or optical sensors. So these sensors give input to the control panel, processor of the control panel, and then this control panel performs some operations on that signal, and then accordingly activation pulses are given to the electric motor. That's how this whole loop operates. So this is a working of the tracking mechanism. There are many solutions to this tracking mechanism problem. This is just a typical tracking mechanism which has this drive component, gearbox component, and electric motor control panel component. So these are the actual snapshots of the tracking mechanism which has been employed in my laboratory here. We have developed a parabolic trough concentrator in our lab. So at that time we have given this, we have provided this tracking mechanism. So this is a worm reduction gearbox. You can see this is a gearbox, Shanti gearbox, and then it has a flexible coupling. Then electric motor, synchronous AC motor of 1 HP. So it works on 230 volt AC. Now this drive is given, so you can see here the magnified view of this part. Here you can see the complete mechanism. So electric motor, coupling, gearbox is connected to a flywheel here, a wheel here, and that wheel drives this aperture. This is the aperture through a cable. Okay, and then the signals are given through this control panel. So this is a snapshot of a control panel. So control panel has many provisions: automatic tracking, manual tracking, pump on, pump off, and all, and emergency off, like this. So a control panel is needed, as we discussed here. So this provides the pulses to this electric motor. There are 5 modes of tracking. So in mode 1 of tracking, the focal axis, we can see here, this is the focal axis of the collector. So focal axis is horizontal. So this is a horizon. This is a horizontal level. It's parallel. So focal axis is horizontal. Its orientation is east to west. So this is east side, this is west side, then this is north and south. So this orientation is east to west. So sun is rising from here, it is setting here. So sun moves like this. And the collector rotates about horizontal east-west axis. So collector rotates like this. So it moves like this. And then it is rotated once. So the collector rotates about horizontal east-west axis and adjusted once every day. So this collector is adjusted once every day so that the solar beam is normal to the collector aperture plane at noon. So it is adjusted, it is rotated like this, so that if the sun is on this side, southern side, then the collector aperture plane at noon on that day makes a normal incidence. So this tracking is just once every day. So this is mode 1 of tracking. Now if we wish to analyze mode 1 of tracking, for mode 1 of tracking, the condition is incident angle theta should be equal to 0 because normal incidence at solar noon. So now with this condition, if we put these conditions, cos theta should be 1, omega solar noon, omega equal to 0, and gamma south facing, aperture south facing, gamma equal to 0. So we know the general equation of incidence angle cos theta. So if we substitute cos theta equal to 1, omega equal to 0, and gamma equal to 0 in this expression, and then if we simplify, so here del is there, beta is there, and then omega is 0, cos omega is 1 here, and then cos omega is 1 here, sin omega is 0. So this term is 0, only these two terms remain, and after simplification these terms remain: sin phi into sin cos, cos sin, and then cos into cos and sin. So sin cos and cos sin becomes del plus beta. So del plus sin of del plus beta, and then cos minus sin becomes plus cos del plus beta. So sin into bracket sin of del plus beta plus cos phi into bracket cos of del plus beta. So this is again sin and then cos. If we recall our multiple angle formula, then we come to know that this comes up, this is cos of phi. Okay, this is phi minus del plus beta. So 0. So cos theta is equal to 1. So theta has to be 0. So this is cos is removed, and then theta becomes 0. 0 is equal to phi minus del minus beta. So beta is equal to, so if we shift this beta here, then beta is equal to phi minus del. So this is the now what is beta? Beta is the aperture tilt to be maintained on any day. So this gives the guideline about what should be the tilt of the aperture on any day. This is for mode 1. So this is the analysis of mode 1. In mode 2 tracking, the focal axis is again horizontal. So the focal axis is horizontal. Orientation is again same, east to west. Orientation is east to west. Then collector rotates about horizontal east-west axis and adjusted continuously so that the solar beam makes minimum angle of incidence over a day. Now here this is not a once adjustment. So collector rotates about east-west axis. So sun, remember, sun is rising from here and it is setting on this. So sun is moving like this. So sun will be at this point in the morning at the horizon, and then it starts from here and then it sets on this side. So the collector has to be continuously rotated like this to adjust the elevation of the sun. So sun's elevation at the horizon in the morning will be 0. It goes on increasing. So the collector also will collector aperture will also be adjusted as per the elevation, and then that adjustment is continuous over a day. So the difference between mode 1 and mode 2 is that the tracking is continuous in mode 2 while tracking is once in a day in mode 1. Now if we wish to analyze mode 2 tracking, so for mode 2 tracking the condition is minimize incidence angle theta. So again recalling the generalized equation of cos theta here, which we already know. Now we have to minimize this theta. So for minimizing the theta, differentiate this equation and equate to 0. So d, and with respect to beta, because we need to maintain the collector, we need to find out the collector tilt. Okay, so with respect to collector tilt, so d theta by d beta is equal to 0. So if we differentiate this expression, and again south facing, gamma equal to 0. So with all these conditions, if we enter tan phi minus, the answer we get will be tan phi minus beta equal to tan del by cos beta. So from this, phi is known, beta we will find out. Now with the input of beta, if we substitute beta in this expression, we will get the angle of incidence for evaluation of the solar energy incident on the aperture. This incidence angle can be calculated. So for in mode 2, the incidence angle cos theta is equal to 1 minus cos square del sin square omega raised to half. So with this we can estimate the amount of energy incident on the aperture, and with this expression we can physically adjust the collector tilt continuously, because that is a function, beta becomes a function of omega. So omega is a time, del is a date, so n day of the year, time of the day, and location. So beta is a function of all these three. Continuously it has to be adjusted. So this is about mode 2 tracking. In mode 3 tracking, the focal axis is horizontal. Okay, so again the focal axis is horizontal, but now it is turned to north-south. Okay, now this is north, this is south, and this is east, and this is west. So now sun is moving from east to west like this. So sun moves from east to west on a daily basis here, and the focal axis is placed north-south horizontal, and then the collector is rotated continuously from east to west. So this is mode 3 of tracking. So collector rotates about horizontal north-south axis and adjusted continuously so that the solar beam makes the minimum incident angle over a day. So this is the most preferred mode of parabolic trough concentrators. This is the most preferred mode of tracking for parabolic trough concentrators. So if we see here, the parabolic trough concentrator which we have developed in our laboratory has the same mode of tracking implemented. So you can say this is a south side and this is a north side. So the focal axis, this is a focal axis. Focal axis is horizontal and the collector tracks from east to west. You can see the side view of the collector. This is the east side, this is the west side. So we have tracked this. So this tracking mechanism moves the collector from this side to this side. So that's how the tracking happens. So this is a mode 3 tracking. For mode 3 tracking, gamma equal to 0 before noon and gamma has to be taken minus 90 after noon. So the condition is to minimize the incident angle. So therefore, for gamma, again the same as previous, we have to differentiate theta with respect to beta and equate it to minimize. So differentiate this equation, incidence angle equation, with respect to beta and equate the same to be 0. So if you just perform this differentiation and then at gamma equal to plus 90, we get this answer. Beta equal to tan inverse of cos del sin gamma by sin phi sin del plus cos phi cos del cos gamma. So you remember this expression to be of cos theta z. Okay, sin phi sin del plus cos phi cos del cos omega is the expression of the cos theta z, zenith angle. Then if gamma equal to minus 90 in the afternoon, we get beta equal to the same expression, the only thing is minus here. So tan inverse of minus cos del sin gamma by the expression of cos theta z here. Now corresponding angle of incidence values can be evaluated using this expression. Cos theta comes out to be sin phi sin del plus cos phi cos del cos omega, the whole raised to 2, that is bracket square, plus cos square del sin square omega, the entire bracket raised to half. So this expression is valid for both the gamma, both plus 90 and minus 90 azimuth angles. Okay, so this is the incidence angle for mode 3 tracking, which is the most popular mode of tracking in case of parabolic trough concentrators. Mode 4 of tracking is again, this is a north-south, focal axis is north-south and it is inclined to the horizon. Now this is horizontal. This is inclined to horizontal at an angle of phi. This is a latitude. So if we incline the focal axis at an angle of phi, then this inclination is called, this mount is called polar mount. Okay, so the orientation is north-south and the collector rotates about, again similar to mode 3, the collector rotates from east to west. Okay, so the collector rotates about inclined north-south axis and adjusted continuously so that the solar beam makes the minimum incident angle over a day. So the only difference between mode 3 and mode 4 is in mode 4, the focal axis is inclined at an angle of phi, that is polar mount. So with this, the amount of energy absorbed increases by a quantum. So this is the actual picture of another flat plate, another parabolic trough concentrator which we have developed for some industry. Now this is a polar mount. So this is a focal axis and then this is the fixture which is made, fabricated, which is mounted, and on this fixture the entire structure of the collector is mounted. You can see how awkward and how heavy is the entire structure. Okay, the approximate weight of the upper part of the collector, including excluding the tracking mechanism, is nearly 600 kg. Now this 600 kg of the structure is sitting on an inclined plane. So you can imagine what sort of gravitational loads in this direction come, because this glass tube also starts sliding along this surface, so it has to be provided stops at every point. So the entire thing becomes very complicated when we go for mode 4 of tracking, and in addition to that, the cost of this fixture increases. So sometimes a designer starts thinking that for seeking a quantum of higher energy input, Is this investment worthwhile? So this trade-off, a designer, a solar system designer, has always to be checked. So in mode 4 tracking, beta equal to phi. So this you can see. So the aperture inclination is equal to latitude. Gamma equal to 0 south facing, and at solar moon omega equal to 0. So the condition is to minimize the incident angle. So therefore again cos theta, if we substitute all these figures here, so the simplification gives us cos theta equal to cos into del plus phi minus phi. So phi gets cancelled and theta becomes equal to del. So the incident angle is nothing but it becomes equal to the declination of that aperture of sun on that day. So this is a mode 4 tracking where there is a quantum increase in the solar radiation input. Mode 5 of the tracking is a perfect. It is a 2-axis tracking because focal axis is north south. So this aperture continuously tracks about east west, and simultaneously it tracks north south also. So in both axes the collector rotates. The collector first rotates about north south axis, about its focal axis, which is oriented north south. So it rotates in this direction as well as it rotates in this direction. So this is a 2-axis tracking, which is meant a perfect way of tracking. So collector rotates about inclined north south axis as well as east west axis simultaneously to maintain normal incidence. Now this mode of tracking is not preferred for parabolic trough concentrators. This type of tracking is preferred for dish type of collectors or heliostat mirrors. So because it is a expensive type of tracking mode, we can say. Now typical comparison, what is the energy gain in different modes of tracking? So this table shows the modes of tracking 1, 2, 3, 4 and 5, and this is the energy gain. So the minimum energy gain is in mode 1. So that's why it is given as 1 point. Okay, so 1 kilowatt hour or 1 unit of energy over a period of time at a typical location, we can say. So if mode 1 gives 1 unit of energy, then mode 2 gives 4% more. So east-west focal axis, east-west, and north once tracking, once in a day tracking gives 1. So continuous tracking about north-south gives 4% increase. In mode 3 tracking, there is 37% increase as compared to mode 1. And then in mode 4 as compared to mode 3, there is a decrease in mode 2 because in some days of year the incidence angle at latitude is less. So the energy gain in mode 3 is much better as compared to the other modes. In mode 5, obvious, it is logical that one will get the maximum energy gain 1.38. Okay, but practically speaking, mode 3 tracking, as far as economic considerations and energy gain considerations, on these two grounds, mode 3 tracking is the optimum mode of tracking as far as parabolic trough concentrators are concerned. Now tracking methodology forms the basis for orienting aperture to the sun. So there are two tracking methodologies. One is, or we can say 3 tracking methodologies one can follow. The first is chronological. Chronological means determination of altazimuth. Altazimuth means the combination of altitude angle plus azimuth angle for the entire year and feeding the values to a microprocessor and controller that drives the tracking mechanism. So it is like this, that if we go behind, we know this expression of cos theta. So this is the generalized expression of cos theta is known to us. We need to find out the altitude angle. Altitude angle is the complement of zenith. So zenith angle expression is this, nothing but this, sin phi sin del plus cos phi cos del cos omega. So for the entire year, we can find out cos theta z, and then in turn the altitude angle. So phi indicates location, del indicates day of the year, phi, del and omega indicates time of the year. So for a location, a day and a time, we can find out the values of altitude angle. Azimuth angle also can be determined, and these values for a minute, you can say, or for each half an hour, for each 5 minutes of say period, these values can be entered into a microprocessor, and accordingly the pulses can be given to the drives of the tracking mechanism. So in this method, so automatically this aperture goes on tracking irrespective of what is the weather condition. So in this method, the collector continues to track the sun irrespective of the presence of the sunshine. Okay, so it's you can see here the sketch of this. Now this is the altitude angle. Okay, so this becomes vertical and then azimuth. Oh, sorry, zenith. So complement of zenith is altitude. So this is the collector aperture, and then we have to maintain the normal aperture has to be maintained normal to the line of altitude. Okay, so this is the altitude, and then in the second view, this view is different. Here in this view, there is a south, this is a ground. Okay, and then here is a top view, we can see. So in top view here there is a south on this side, and then north, east and west. So gamma. So collector azimuth, aperture azimuth has to be adjusted. So simultaneous adjustments of alpha and gamma are done here. So this method does not take into account the momentary coverage of sun by the clouds. So sometimes a cloud cover comes, for say a patch of cloud covers the sun, and there will be shadow on the collector. But this chronological method of tracking, it doesn't take into account that cloud. It goes on continuously moving at a speed of the sun, and it traverses its motion till the end of the day. Many times long spells of shading also may not be accounted. So thus incurring power loss, because tracking system is on. So tracking mechanism is consuming power whether there is a shade on the collector or not. So this incurs the power loss. So this is not a desirable thing. And again, refinement in focus due to misalignment of backlash is not possible, because many a times you can see here in this huge structure, if we track this mechanism, there will be backlashes. And say, for example, from east to west, this aperture tracks. Sometimes, suppose this aperture overshoots, then we need to refine the adjustment of the focus. So this type of adjustment, minute adjustments or refinements, cannot be done in this type of methodology of tracking. Okay, once the aperture moves forward, it cannot be taken back. Okay, so this is of course when once we put that tracking is in automatic mode of chronological methodology. Okay, so only chronological methodology for tracking is not desirable because it has its own or inherent disadvantages. On the other hand, second sensor-based methodology is also used for tracking. So what happens? One or more sensors. So as we have seen here in the first of our of this presentation here, sensors are placed here on this side. So there will be one or more sensors placed. So one or more sensors installed on the aperture plane, they sense the absence or presence of sunlight, and then accordingly pass on a signal to the activating device for tracking. So if sun is there, they will move. If sun is not there, they will not move. So accordingly some logic is developed for depending on the shadow and presence of sunlight. So with this method, start of the day operation, so when to start the day, and end of the day operation, when to end the day, and fine adjustment in focus can be precisely done. So with sensor based method, these are the advantages. However, what happens when the wind blows accidentally, if the sensor is shaded due to some falling leaf, some leaf falls on the sensor itself instead of that collector. If it falls on the sensor, then what sensor will sense? It will not sense sunlight. So it imagines that there is a sun, or there is a day end. So it will not move. It will be stationary, but still it may be at 11:30 in the morning. So some falling leaf or some flying stray object, it falls on the sensor, or some building shadow falls on the sensor, then it will give a wrong signal. In that case, the operator has to see that and reorient the system at that time. So this is the disadvantage of the sensor based system. So in sensor based systems, these light dependent resistors, this is a LDR, this is a snapshot or photograph of a LDR, and this is the symbol of the LDR which operates on the light. So light dependent resistor, which is called LDR, and optical sensors with rotary encoder strips are used in tracking controls. So the resistance, so in case of LDR, the resistance of the photoresistor decreases with increase in the incident light. So when the light falls on this LDR, its resistance decreases. In the dark, so what is the scale of this decrease? So in the dark, a photoresistor can have a resistance as high as several mega ohms. While in the light, a photoresistor can have a resistance as low as a few hundred ohms. So the range is wide so that the control will be easy. That's why LDRs are preferred in tracking mechanisms, because from several hundred ohms to mega ohms, we have a range available over a control of intensity of light. Now, an optical sensor converts light rays into an electronic signal. Okay. Now, how normal incidence is maintained in sensor-based tracking methodology, that is explained with the help of this sketch. So this is a small, you can say a plate. This we can call it as a small base plate. On this base plate is mounted on along the aperture plane of the aperture. Okay, so this is a parallel to the aperture plane. Okay, and then on this base plate there is an optical strip which senses the shadow and light. Now at the so optical strip is fixed on this base plate in a circular. It is a circle, and this circle indicates the acceptance angle of the collector. Suppose acceptance angle of the collector is 1.5 degrees. So then this radius indicates with the in relation to this height of the pin, this radius indicates the acceptance angle. Okay, so this radius, shadow radius, indicates the acceptance angle. So a pin is fixed at the center of this optical strip circle. Now when sun shines, when sun is over this pin, okay, so it casts a shadow on the base plate. Now if the shadow of the pin touches the optical strip here, it indicates that the collector or the aperture has moved out of the acceptance angle, and then accordingly it gives the signal to move towards inside, and then the aperture moves in this side, and then the sun comes here, and again the length of the shadow will be less. So the activation signal is based on the length of the shadow should always be in between this circle. So shadow should not go beyond this circle. That operation or that control is maintained by this optical strip. That's how normal incidence within the acceptance angle is maintained in sensor-based control systems. Now, which type of optical sensors or optical strips are used here? So, typical photograph of an optical sensor is, this is an industrial optical sensor, is shown here. So, an optical sensor converts light rays into an electronic signal. The purpose of an optical sensor is to measure a physical quantity of light, and depending on the type of the sensor, it translates into a form that is readable by an integrated measuring device. So optical sensors are used for contactless detection, counting or positioning of the parts. So shadow position is sensed here, and accordingly signal is given. So we have discussed two methodologies of tracking used. One is chronological and then second is sensor based. The pure chronological as well as pure providing a pure sensor based is not a practical thing. So in actual practice, a combination of chronological and sensor based tracking control system is preferable. Though it is a costly, because providing both systems and providing both controls in a microchip is a bit costly, but it is worth providing a combination of chronological and sensor based systems. So with this we stop at this point of time, and topic of concentrator will continue, and the topic to follow are optical and thermal analysis of compound parabolic collectors and then parabolic trough collectors. We have identified two types of concentrators for optical and thermal analysis, which are the most popular and most prospective collectors for the development of industrial process heating. That's why only these two collectors are chosen for analysis. Those who are interested to take a project or take a research or take some sort of analytical study, we can independently study the thermal and optical analysis of heliostats, thermal and optical analysis of linear Fresnel collectors and all other versions. Okay. So once we complete this part, we will go ahead with the performance analysis of the above concentrating collectors, followed by thermal energy storage. Thank you.